Hello everyone, my name is Martin Fouilleul. This video is the first of a small series of devlogs I'll make as I work on my project for the HMN Network Wheel Reinvention Jam. The Jam is a 7-day event to reinvent a wheel in software. It's organized by the HMN Network community, and you can find the links to the HMN Network website and the Jam here in the description of this video. If you happen to watch during the Jam week, you can also feel free to ping me on the HMN Network Discord. I'll be working on a live coding tool. There are a number of wheels that exist and that can be reinvented in that domain, like graphical programming environments like Max MSP or Pure Data. There are great tools for prototyping quickly and testing audio IDs, but I'm not a great fan of the mouse-heavy UX and the way you have to manage explicitly a node graph of small black boxes and moving around all those boxes and drawing cables between them. And furthermore, I find it imposes a data flow paradigm that is okay for most DSP algorithms, but it's not great if you want more imperative control and if you want more temporal constructs, for example. We can also talk about Super Collider, which is a server-client architecture. The server is a synthesizer that you can control from the client, which uses domain-specific language. You can also pilot the server directly by sending OSC messages. And so you don't have the drawbacks of having to move those boxes around and connect them, but it's still a node graph under the hood, and you're still restricted to a data flow paradigm. There are also solutions like FOST, which stands for Functional Audio Streams, and it is a language that allows describing DSP graphs. It's an interesting language with a number of great features like automatic documentation generation, integrated GUI, and it's really a good tool for prototyping quick audio IDs, but it's still a declarative functional data flow language, and the syntax can be a bit cryptic sometimes. So if you want more imperative control, it's not that great. So what I will try to do during this week is set up a bare minimum live coding environment for audio. That is to say, the system will have to handle audio devices and choosing your audio formats, and it will just hand you input buffers from which you can read and which you can process, and it will provide output buffers in which you can write. On top of that, the system will expose some helpers for common DSP operations, like buffer operations, delays, simple filters, we'll see. And it will also have an integrated GUI system to quickly make boxes, buttons, checkboxes, and sliders, and so on. So a pretty minimal tool, but pretty flexible, I hope. So I don't exactly know how much of these goals I will achieve in 1 week, because this is my first jam ever, but I'm really excited to find out. So let's get to work. So here I have set up a simple application using my platform layer, which is called mileposts. So I include the header for the platform layer here, and then in my main function I will load a font file for the GUI. I init the platform layer here, and I create just a simple window for which I create a surface to draw on a graphics context, which allows to draw using a vector graphics library. I create the fonts for that specific graphics context, and I initialize my application structures, and I initialize the style for my application GUI. Then I set up an event callback. I bring the window to the front, and I enter the event loop. The event loop is quite simple. It just forwards most of the events to the GUI, and it handles events such as close, resize, and frame events. And on frame events we call the GUI functions to draw our widgets. That GUI functions is really simple for now. It's just a single view. So I begin frame, I push my custom style here, and I declare a view in which I can then add widgets, but it's empty for now. So here we are with is one GUI view inside. So now I'll move on to coding a simple audio output to this application. Okay, so now I have some audio outputs working. So I have these functions that initializes the audio format, and then I call audio init outputs, which initializes the audio output of the application. The audio format is set to default values for now. So I have sample rate of 48K, 2 channels, and 256 samples per buffer. I also set the macOS specific audio format here. Then my audio int output function creates an audio unit hardware abstraction layer, which is the audio unit that's used in core audio to communicate with sound devices. So I create this audio unit, I initialize it, I set its format, and I set its frame buffer size, sample buffer size, sorry, and then I just get the default output devices. It will be the device which is selected in the preference panels. And I set the output device of the audio unit to that device. And then I can register a simple callback that will be called when the device needs output buffers. And then I start the unit. My render callback is here, and I'm just doing a very simple sine wave here. So for each sample, I compute the value of that sample using a sine, and then I fill all outputs buffer to that value. So that's it, basically. A very simple application. That's just outputting a pure tone, so nothing very exciting, but it means that our output is working. So now I will try to add an audio input to get samples from the microphone. This is a quite involved process because apparently you have to create an audio unit for an output audio unit, and then tweak its parameters to transform it into an input. So it's described in this document, so I will try to follow that documentation, and we'll see if I get some inputs here. Okay, so now I've got the input working. It was a little bit trickier than I expected, because as I said, it's almost the same as for an audio output, but not quite. So there are some subtle differences, and the naming is quite confusing, and also you must call the same kind of functions but in a different order from the outputs. So and it's not very well documented. So it took a little bit longer than I thought, but here we are. So we create an audio output unit, and then we turn it into an input by enabling its I/O on the input scope here and disabling the I/O on the output scope. Then we can set the input device. Then we can set the format, but if we set the format before the input, apparently it's not working. Then we can set up our input callback, and I will talk about the input buffer list a little bit later. And then we can initialize at the end remember that in the audio output we initialize at the beginning, and then we can start the unit. So here we allocate an audio buffer list because the way the callback works is a little bit different from the output. So if we see here, if we take a look at our input callback, the input callback is called when the device has some data to handle to you, but it doesn't give you the data in the IO data parameter, as you could expect. Instead, you must have somewhere an input buffer list, and you must call audio unit render and pass it your buffer list. And then you can read the samples from the buffer list. So I'm doing exactly that here. I have allocated my buffer list when I initialized the audio input. So I call audio unit and render, and then here I just print some. I just print the first sample of the first buffer just to have some output and show that we have some signals. So here we go. So we still have our input and we have seemingly random samples here. Okay, what I will do next is that we have a bit of a problem because the input callback and the output callback are registered to different devices, and they are called from different threads. So you can't really communicate between the two in an easy way, and I think it would be it's important to have functions that take inputs buffers and gives output buffers. So if we want that kind of function, we have to somehow pass the input buffers from the input callback thread to the output callback thread. So I think we will have to implement some kind of circular buffer. So that's what I will do next. Well, I have implemented the ring buffer. So it's a very simple single producer, single consumer queue. There's just a channel count, a cap, mask that is used for wrapping around the buffer, and two atomic read and write indices, and the data for the buffers. I have functions for initializing the buffer, cleaning up, and writing samples to the buffer, as well as reading samples from the ring buffer. So now I used this ring buffer in my input callback. I call audio unit render to get the samples from the audio units, and then I just write them to the ring buffer. And now in the render callback, I read samples from the ring buffers in special buffers that I call DSP input buffers that are allocated at initialization time. And I have also DSP output buffers that holds the pointers to the to the output buffers that are passed to our render callback. And then I can call my DSP function that takes a channel count, a buffer size, and two lists of input and output buffers. So to test that it is working okay, I just wrote a simple myDSP function. As before, it's computing sine wave, but it's modulating the sine wave with the input samples. So it's essentially ring modulation on my voice. So we can test that. And we can see that my voice is modified and is ring modulated. Okay, so that's great for now. Okay, so let's recap what we did today. I wrote a simple application with one window and one empty GUI view. I added an audio output and an audio input, and I linked the two through a ring buffer. And then we did a little demo of ring modulation effects using our simple setup. So I think we're in a good position to start tomorrow to add the hot reloading capabilities after maybe a little cleanup of the audio. So that's it for today. Let's wrap it up and see you tomorrow.